Hi everyone, welcome to Modern Optimization Methods. Today we will introduce the third part of Chapter 7. We introduce by two examples to show the first-order optimality conditions. Now let's take a look at the first example. In this example, we also have minimized the sum of two components subject to one inequality constraints. Here, notice that different from the previous example in previous chapter, we can see that here we got a feasible solution as a disk, okay, which is around the origin. Then we can see that the gradient is also along this direction. However, we have different cases for the gradient of constraint. Let's discuss two cases. Firstly, if we are standing inside of this disk, okay, which means that we stand in the interior point of this feasible region, then if we try to move to get a better solution, then of course we will move negatively along the gradient direction. Moreover, we have to maintain the feasibility of the point. Therefore, we have to consider that when we move along this direction, the next point must be kept inside of the feasible set. Okay? So if we're standing here, then any directions within the n-dimensional space is all feasible. Therefore, for this point, it means that we only need to consider to get a feasible reduction point. We do not have to consider the feasibility. However, if we are standing at the boundary of this point, then we can see that in order to get a better function values, we need to move along negatively with the gradient direction, okay? However, meanwhile, for the feasibility issue, then this direction S has to satisfy some constraints, okay? So S cannot pointing out outside of the feasible region. In contrast, S can only pointing out inside of the feasible region, okay? So this means that different from equivalent constraints, we have more constraints on the search direction to keep the feasible point of next point, okay? Now, to make a brief conclusion, we can see that the optimal value can still achieved at the left bottom of the point of the region. However, for the relationship between the gradient and the gradient of constraints, we have that they must be lie in the same direction. In other words, the parameter lambda 1 here must be positive or 0. It cannot be a negative 1, okay? So this is the difference from the previous example, all right? And if we are standing at the boundary point, then we need to be careful with the search direction, because if we cannot choose the search direction properly, then we may jump outside of the feasible part. All right? Now, let's make further analysis in a mathematical way. Assume that we are standing at a feasible point which is not optimal. Then let's take a look at what is the direction S have to satisfy, okay? So for the small step S, as we mentioned before, it has to satisfy the reduction in function f, which meaning that the inner product of the gradient of f with S must be strictly smaller than 0. On the other hand, the direction S has to keep the feasibility condition. So for the feasibility condition different from equality constraints case, for inequality constraints case, we require that C1 x at x plus s must be greater than or equal to 0. So if we do also first order expansion to do the approximation, then we can get that this term will need to be greater than or equal to 0. Now we have two terms here, okay? So we have to discuss two different cases. The first one, okay, is that if this C1x is 0. And the second one is if this C1x is not 0. All right? Below we discuss the two cases one by one. In first case is that if we got this C1 at x is strictly greater than 0, meaning that this point lies strictly inside of the feasible region. In this case, then actually if s is small enough, then we can always maintain the feasible direction. Okay, so in other words, in this case, s can be any direction as long as it is small enough. So this is a simple case, actually. Another one is that if x lies on the boundary of the constraint or the feasible region, in this case, it is similar that we got C1x to be 0. Therefore, the feasibility condition reduces to this one, okay, which is different from the equality constraint case. Because here you got the inner product of the direction with the gradient of constraint to be greater than or equal to 0, all right, meaning that this direction has some constraint. You cannot move anywhere. You can only move along inside of the feasible direction, okay? Therefore, for the second case, the feasible region and the function reduction actually gives the direction s that it has to satisfy the following two conditions, okay? So for the first one, as we defined before, it is an open half space. And for the second one, it is a closed half space, okay? So the intersection of the two parts will be the direction that we can move forward. Now, as we mentioned that if we take another point of view, that we assume x star is a local minimizer, then such direction will not exist, right? Because if it exists, then we can move forward and will violate the fact that x star is a local minimizer. So S exists if and only if the gradient of f and the gradient of constraint c are not in the same direction. Okay, so this is an if and only if relationship. In other words, if the direction of gradient of function value is the same direction as the function value of constraint, then we cannot find such direction. In other words, if S is a local minimizer, then this condition will hold, okay? So this actually leads to the first order optimality condition for one inequality constraint case. Notice here that if the two vectors, they are in opposite directions, then the intersection of the two regions would be an entire space, meaning that for this case, we can always move forward to get a better functions, okay? Now we demonstrate this again by the previous figure, meaning that if x lies strictly inside the feasible direction, we can move any directions to keep feasibility, okay? And if S is on the boundary, then we cannot move outside the feasible region. We can just move toward the direction inside the feasible region, okay? Now, let's give the conclusion here. So for one inequality constraint case, if X star is an optimal solution on the boundary, then the relation here needs to be satisfied, with the coefficient lambda 1 must to be non-negative, okay? And in other words, if X star is an optimal solution on the boundary, then there must exist a lambda 1 which is non-negative, such that the condition here needs to be held. So if X is an optimal solution lying inside of the feasible point, then we can actually see that if we take lambda 1 to be 0, then we can get that the gradient must to be 0, okay? So this actually also happens. Now, let's make a summary about the above two cases, that we define also a Lagrange function for the inequality constraint, which is actually similar as the equality constraint case. However, if X star is a local optimal solution, then the condition here are different, okay? So the first condition is the Lagrange function. If we take gradient with respect to X, then we have it is to be 0 for some non-negative lambda. And the second condition is actually this one. It is called complementarity condition, meaning that we got the lambda I multiplied by the constant of C at this point to be 0, okay? So the two conditions here actually unifies the two cases as we just discussed. Now, let's take a look at the case that we have two inequalities or multi-inequalities. If you got two inequalities here, and we can write the Lagrange function by adding one extra term here, we minus lambda 2 multiplied by C2, okay? So this is the Lagrange function. And if there is no first order feasible direction exists for this example at some point, then we must have the following result. The gradient of Lagrange function with respect to X is 0 for non-negative lambda 1 and lambda 2, all right? Moreover, we require that for each inequality constraints, the complementarity condition holds for each of them. So this is actually give us how we extend one inequality condition case to the two inequality condition case or multi-case. Now, let's make a brief summary about this part. We introduce the case that how we derive the first order optimality condition for the two inequality case, and we derive the optimality conditions. In the next part, we will formally give the first order optimality condition. Now we stop here and see you next time.